As Tay just said, I've really enjoyed lunch. Thank you for having me. It's so good to be back at JSConf Budapest. It's been 6 years since my last time returning to Budapest and to JSConf, so thanks again for having me. It's good to be here. Nope. Spoilers for later. Welcome to my talk, Offline First IoT, all about building connected devices without relying on the internet and powered by JavaScript. So as Tega said, my name is Hehr. I'm a staff software engineer on the front-end platform team at Betterment, which is a financial robo-advisor in the US. Despite the robo part of that description, I don't work on IoT for my job. This is just a side project and a hobby. I have been an active and empathetic contributor and open source maintainer in the past, and since the beginning of my career. Occasionally, given that opportunity to help maintain some of the projects that I've contributed to. And I like to spend time away from the computer, not working on IoT and other things, on long bike rides and at my local climbing gym. So here's what we're going to go over today. The table of contents, by the way, is TOC. So we're going to talk about a little quick overview about IoT in the real world before covering what the heck I mean by offline first, if you've never heard of that before. And then we'll dive into how we can build IoT devices offline, and how JavaScript can help out with this. And then finally, we'll wrap up with what you can look forward to and how you can get involved with this whole process. So let's start with the state of IoT in the real world. I think most, if not all of us here and maybe online, are familiar with the phrase Internet of Things. It's generally associated with like the smart home and remote sensors and controls on embedded and internet-connected devices. The Iot ecosystem is often an easy target of ridicule, and given some weird ways it can fail or be oddly integrated into everyday life. I don't think I ever want to see an email like this telling me that some sort of thing that my pet depends on is going to have a service outage. And as much as we like to make fun of these broken experiences, many of the working use cases end up connecting the world to our most private spaces, intentionally or not. This default behavior of most smart home integrations doesn't sound very smart or safe to me. Along with the security issues, this dependency on the stable internet connection prevents our gadgets from being resilient to the realities of practical usage in our homes. I like to call this diagram, how many services does it take to turn on a light bulb? The services behind our devices put unnecessary delay into the operation of these components for the roughly 10% use case of controlling them outside the local network. Not to mention the unexpected obsolescence when those remote services are deprecated or shut down entirely. This is Insteon, which basically we shut down completely overnight. It was so bad that the CEO wiped his history from LinkedIn, that he never worked there ever. So I'm sure there's a whole big story about that. That just happened recently. And this is where the offline first philosophy comes into play. So I've said this phrase a few times now. Offline first. Folks may have heard about mobile first during the early days of responsive web design and mobile app development, which was followed by offline first back in 2013. Offline first is the idea of treating a network connection as a progressive enhancement for our applications, not that they should always or only stay offline. Many native applications operate in this manner because they are embedded into the device or operating system with no guarantee of internet availability. Web applications assume the opposite because it takes an initial connection to get the app onto your device in the first place. But that's not assured to be true from that point onwards. So introduced in the early days of HTML5, when application cache and local storage and web SQL were the state of the art. These days, we have improved tooling in the form of progressive web apps, using service workers and newer storage APIs, advertising the advantages of installable offline web applications. I learned about the offline first way of development while contributing to Hoodie. There we go. Contributing to Hoodie, which uses CouchDB as a client-side data store that would sync with an external CouchDB when a connection was stable and available. This architecture also allowed the client side to react to certain events and changes in that data store through those events emitted by CouchDB and Hoodie itself. So as I said before, we want to treat being online as a feature rather than the ability to go offline as the feature, offline first expectations. Connectivity and data freshness should be communicated to the users, provided sensible fallbacks, rather than showing an endless spinner or an error page when an unstable or there's no internet connection at all. Syncing data stored with new remote data, that local data with the remote stuff, will always have conflicts or will have conflicts eventually. So you should be prepared to handle them either by presenting that to the user, let them choose what's new or what they want to keep, or by some other strategy you want to entail. Working this way on the web has heavily influenced the way that I think about internet availability and how much our devices rely on them by default. So how do we apply this idea of offline first as progressive enhancement to the Internet of Things? So these are my general guidelines when I like to put connected devices and services into my own home or any sort of personal private space that I have. So as I said before, so there should be a physical fallback. This is always a need for me, especially anything that should be key and important. This can be turning on lights, unlocking doors, all that sort of stuff should be able to available, again, offline, either by a physical fallback or by being able to sync remotely through some other source locally. Communication with the device should be, again, local on the local network by default over preferring an external service. Any connection outside that local network should be secure, preferably end-to-end encrypted, and approved by the owner of that device, permission-based. We're very used to that on the web when we want to access some sort of part of the user's data in terms of their location or navigation, any of the sensor stuff that we saw previously should be approved by the person who's going to be affected by it. And then use of outside services should be seen as progressive enhancement, so having that sensible fallback when it's not available. And then any over-the-air updates should be opt-in unless absolutely necessary for security patches. As we saw before, if you have a service outage because your microwave or your coffee maker tried to do a Wi-Fi update in the middle of trying to make something, that just doesn't feel good. So how can these connected devices communicate without the internet? I mean, what are they actually connected to at that point? Well, there are many ways available to us, ranging from direct one-to-one messaging. We have pub-sub models, publisher-subscriber, and even mesh networking available to us on the local network. And each strategy has its pros and cons. So direct communication could also be called client-server communication, and this is the relationship that they hold with each other. An HTTP server could be running on a local device that is exposed to the network, and clients can send those requests to it as long as they know, the IP address or maybe a local host name. Similar to that, Bluetooth devices can advertise and have multiple clients connected to them in order to receive information. We'll talk about discovery a bit later, but that's one of the core downsides to this approach, since these devices or services need to be aware of the available servers and hosts to manage those connections manually. Pub-sub, or publisher-subscriber, communication provides a way of emitting or listening to information without a direct knowledge of the source of that information. While WebSockets could be considered pub-sub based on their usage, they have a direct client-server relationship in terms of how they connect, and they require that connection management exactly. Multicast Udp allows for a fire and forget pattern of communicating over the IP on the local network, and has resiliency to devices or services disconnecting or joining the network at any point in time. Although it lacks some reliability, since there's no required acknowledgement from any of the receivers when they send that message. As I said, fire and forget. That's where MQTT really shines as a messaging protocol that requires a centralized broker, but has stronger guarantees around if and how many times a message is delivered. It's quite popular in the IoT space, including brokers like Mosquito. The broker's piece usually becomes a point of friction since it requires an additional long-running device on the network in some way. And then mesh networking is one of the newer and more popular forms of getting into IoT communication, because this allows for nodes or devices or services to connect directly, dynamically, and non-hierarchically to as many other nodes as possible, and then they cooperate with one another to efficiently route data to and from different clients. Z-Wave is a proprietary mesh protocol that requires specific hardware to communicate over a lower radio frequency than Wi-Fi. So it uses less power while shipping smaller packets of data over time. Zigbee is based on the same frequency as Wi-Fi while providing a low-power protocol built upon low-rate wireless personal area network, or LRWPAN, which provides the building block for 6 low WPAN, or IPv6 over low-power wireless personal area networks. This is used by Thread. And so Thread is quickly becoming an IoT standard through an industry working group including Samsung, Google, Apple, and many more. It provides stronger encryption, IP addressability, and self-healing reliability. As I said before, we need a way to discover these various devices on our network. We don't just always have a domain name to go hit, but we sort of do. So one of the hurdles in creating resilient services is that they may appear or disappear from the network at any point. Domain name system service discovery, or DNS-SD, falls under the ZeroConf or zero configuration networking set of technologies. It allows clients to discover a named list of service instances and to resolve those services to host names using standard DNS queries. It was proposed at Apple in the 90s and implemented in 2002 under the name Rendezvous, later changed to Bonjour. They really like the French names for this sort of configuration, it seems like. DNS-SD is advertised over the local network through Multicast Udp, as we described before, called MDNS, so Multicast DNS. And it is resolved to the .local TLD. So if anyone's ever seen something on their network or been able to connect to like mything.local, that's over MDNS. It was used by Apple for local server and peer discovery for applications like Safari, iChat, Messages, as well as seamless AirPrint support. So our printers, generally these days, are serving some type of local server and advertising themselves to other devices in order to say, like, hey, you can print to me, here's how to connect to me, and here's how to communicate. It's also supported by many Linux distributions through the Avahi driver. And there is Bonjour for Windows, which usually used to require installing iTunes in order to make that work. So as I said before, I like some of the Apple devices because they already advertise this type of stuff. And so HomeKit uses its default behavior of communicating only on the local network and then delegating any sort of remote communication through a hub. And so those hubs can be an Apple TV, an iPad, a HomePod, any of those types of things that just stay in your network and then are end-to-end encrypted as far as the communication with any of your devices outside of the network. And HomeKit currently operates over MDNS for discovery and uses HTTP for communication or Bluetooth for both sort of responsibilities. And here's where you clap when I drink. Thank you. And as Tiger said before, he mentioned Home Assistant. Home Assistant is another way to add that sort of local first communication and control with some additional flexibility and expanded options due to the open source community that provides integrations to this software. However, it takes a bit more know-how and expertise to manage it correctly. You have to have some sort of device that's always running it, and so that's a bit of server management, and not everybody's ready to get started with that. Although Home Assistant does provide a system for integrating with Z-Wave, Zigbee, and MQTT, which HomeKit currently does not. All right, so finally get into the JavaScript part of this. We're at a JavaScript conference after all. So how does this popular language fit into the world of IoT? Well, starting off, we have a very capable server-side environment for Node.js that can be used to control headless Linux devices like a Raspberry Pi, or I'm very preferable to the Tessel 2, among others. The Tessel 2 was an open source hardware project that I helped contribute to and maintain that provided a friendly onboarding experience, handy APIs for working with wired, also known as pinned, or pins, and wireless communication. That's all the sort of networking stack that we had available, while supporting most of the NPM ecosystem. Packages such as Johnny-Five allowed you to control all sorts of sensors and peripherals across many development boards, including the Tessel 2. These devices are relatively small. I have a few of them on stage today. Compared to traditional servers or laptops or any sort of desktops that we have available in our home, while consuming much less power to boot. I'm currently powering several right now just off of regular USB batteries. But how about supporting even smaller form factors like microcontrollers that don't include an operating system that can be powered off of a tiny LiPo or coin cell batteries? This environment is usually reserved for system languages like C or Rust or C++. Well, Custom JavaScript engines for embedded devices are actually not very new at all. My first experience with them was with the Pebble smartwatch, which ran a fork of an engine called JSConf, which was provided by Samsung. This enabled for full-stack wearable JavaScript applications that could run on your phone and your wrist. The Asprino project has been around since 2012, and actually has its own smartwatch as well called the Bangle.js, and they just recently came out with the second one. So if you want to have a wearable JavaScript application on your wrist, check that out. Each of these implementations come with caveats or limitations for developers who are used to modern JavaScript APIs in the browser and Node, such as promises, async await, classes, etc. This assumption has changed with the introduction of Moddable XS in 2017, and I'm obviously a little bit biased there. Moddable is focused on shipping a spec-compliant engine to microcontrollers, currently supporting ESP8266, the ESP32, and the Raspberry Pi Pico boards, and providing APIs for interacting with common sensors, peripherals, wireless communications, and displays. It has been used in production environments including appliance displays like microwaves and ovens. It is also the first, if not only, engine to implement ECMA 419 standard for JavaScript APIs on embedded systems. Who here has heard of ECMA 419 before? Okay, no one as far as I can see from here. Well, TC53 is the technical committee behind ECMA 419 and was formed in 2018 to focus on the ECMA 419 standard. I attend TC53 as an invited expert through my experience with Tessel. And TC53 is bringing the benefit of standard APIs to embedded systems so creators of hardware products can benefit from rapid development and scalability enjoyed by web developers. To achieve that, TC53 is focused on its efforts on JavaScript and uses JavaScript to expand beyond the web into embedded systems powered by resource-constrained environments and devices. Unlike TC39, TC53 doesn't have any sort of formalization of stages of proposals just yet, as we heard about through the types as comments or type annotations proposal we heard yesterday morning. But there is work to share annual updates to the spec each year. The first version, shown here, contain information about peripherals and sensor interfaces, while this year the committee has been working on further refining those interfaces and adding additional initial networking APIs, which I really care about. ECMA 419 heavily uses classes and methods for event listeners, which could be contentious for a lot of typical JavaScript developers. However, this interface makes it easier for implementers and library authors to layer on top of it. One such example is Johnny-Five Embedded, or J5E, and takes advantage of this approach and provides a more friendly and familiar API to anyone who's used to Johnny-Five or more modern approaches to JavaScript, and working with all sorts of hardware components. Another example is building on the upcoming networking APIs of ECMA 419 is the implementation of Fetch, available on embedded devices through Moddable. So now Fetch will exist in microcontrollers, in Node, and in the browser. So Fetch has finally happened. It's there, it's everywhere. All right, so let's dare the demo gods once again today and attempt to show off the concepts that I've just been talking about. But first, a tiny story. So this is about a HomeKit clapper. In the summer of 2019, I just moved to a new apartment with a bedroom that had no overhead lights and no convenient switches for the available outlets in the room. Since I was renting, I wasn't about to go do some electrical work into the room, but it was becoming quite annoying to stumble through the dark in order to activate a light when my wife would joke about being able to clap on the lights. So for anyone who has not heard of the clapper before, this is a gadget that's been around for quite a long time and sits in the outlet and listens for claps to toggle the power on. This device still exists today. You can buy it anywhere. And while that could work for my use cases, I want to be able to also control it from my phone. So this is when I looked into kind of one of the gateways of getting into IoT, which is a connected outlet or smart outlet, rather than replacing all the different light bulbs within my home. And it doesn't require a separate hub to work. You don't need to ever worry about it running out of power because it's just always on. This enabled me to use HomeKit to control the outlet, so I looked to my shelf of devices to figure out how to trigger it with sound. As I said, I'm a little biased towards my Tessel 2 development boards and its associated light and sound sensors that are available as pluggable modules. Now, how do I send this information to HomeKit or just the outlet? Enter Homebridge. So Homebridge is a very capable Raspberry Pi. I could write a plugin in JavaScript. Homebridge runs in Node.js to communicate with my Tessel. So rather than depending on an external service, like I mentioned before, like Adafruit IO or Azure IoT Hub, which are fine services for more expansive use cases, I wanted to stay local and keep my messaging offline. So I could create a plugin that ran a local web server, that could hit an endpoint for toggling the light, and that would require some knowledge about the IP address of the Raspberry Pi running the server, or multicast DNS local host names, as we mentioned. But to keep these two devices completely separate and resilient to the ups and downs of network communication, I chose to go the pub sub route through Multicast Udp. And for those who have never seen the dgram module, it's been around in Node.js since nearly the beginning, and is the building block upon which MDNS is built for Node.js services. This is how Homebridge actually advertises itself to HomeKit. I wrap this module into a reusable, familiar event emitter interface, so any device on the network could subscribe to and emit events just like any other component in an application. So let's take a look at the tiny bit of code that I have available today. So this is the program that's running on a Tessel that is currently sitting up here with me right now, not in the box. And so we're going to pull the Tessel module, which actually lives on the device itself, grab the ambient sensor package, which is available on NPM. We literally print the NPM package name on the device itself, or the module. And then the multicast eventer package that I made and just pulled into this program. And then we're going to create a new sensor object using the port on the Tessel, and a new instance of our multicast emitter that we'll just call our publisher. And we'll set some thresholds for what sound would then trigger the event on the sensor, as well as how long we want to wait between claps to do the double clap inspired by the clapper. And then we have some kind of state management in here to track some stuff. And so we're going to wait for the sensor to tell us it's ready to start listening for events and for sound, and then set that configuration to our threshold or trigger level. And then on the event of the sound trigger, which will happen once we reach that threshold or pass it, then we're going to clear it out and then reset it again to set up another listener. And then once we have, if we have a first clap state, then we're going to clear any timeout that we have and then emit the clap event on our publisher and then set the state back to no claps. Otherwise, we're going to set our first clap, which means now we've just heard the first one, and set a timeout to see if we don't have another one within the threshold amount of time, then we're going to reset it back to its base state. All right, so you've been very patient. It's time for a demo. So we're going to see, I'm not touching anything. Ta-da! So that is actually, this little device is running behind the box with my Tessel, and it's just a little sensor running on battery power. And I'm not running on any internet connection except for one Wi-Fi network that's running off of a Tessel over in the corner over here. So this Wi-Fi network is currently called offline first, of course, and not connected to the internet whatsoever. It's just a shared backbone for the wireless. And the last demo is a more recent prototype that was motivated by the time at home with my wife during the pandemic. She would never know when I was on a video call because I had this screen that blocked me from the rest of the apartment. So I explored building a connected on-air light to help communicate this status whenever my webcam was active. So this is what it looks like, as you can see on stage for those who are up close. It's literally a paper prototype. It's made out of a box I got from Adafruit. I carved in on air on there, put some paper in front of it, and it's filled with this. It's not much to look at, although I was very careful going through airport security, as Tiger had mentioned earlier as well. You don't like to see wires poking out of stuff, so you gotta be very careful, and the battery was not connected whatsoever. And so this right here is actually being served by the device in front of me. This is actually an iframe going to onair.local within my local network. And it's just running off of a USB battery, and it uses just a regular form. There's no client-side JavaScript actually running this at all to trigger the form controls and HTTP responses. So as we see here, if I go and click on the light, we should see the light come on. It's a little tough since I'm getting a bunch of stuff here. Let's go over to the, so here, light's on right now. There we go. Lights off, there we go. I can control also the color here. So now we have a blue light. And now the real trick is, does my webcam work? So luckily I'm using SlideDev, if those who have never used it before. And there's a nice little view here, which will pull up my webcam. And we can see here, the light is now on because my webcam is turned on. Here, I'm gonna show that over here. It's on. I have not touched the form at all. I've just only touched the webcam itself. The webcam's off. And now my on-air light turns off as well. So this is all running using a background process I have written in Node.js as well on my computer that just is looking for events that are streamed through macOS to say when my webcam turns on. It then will send an API response to the local web server running locally and then triggers it on and off. It's been great fun to build on it, and I hope to make it even more resilient as well as we did with the clapper. So where do we go from here? So I want to really improve the starting experience for any new developers to embedded environments and working with these newer APIs and newer systems. So I created a CLI called XSDev to help make automating the setup and usage of Moddable much easier and much more expected by folks who are used to using like create React app or npm or npx create blah, right? And so these 5 commands allow you to install that CLI globally, set up the initial tooling for your environment, whether it's macOS or Linux, and Windows support is coming soon, and then also set up the necessary drivers and everything needed to build stuff for the ESP32, which is what I use to run in my on-air light. You can also have it set up for the Pico. There's a WASM support as well to run certain prototypes in the browser. And then you can create a new project where I called this one Fetch Happened, and I can use an example template from Moddable in order to just create the initial sort of code that you can run on your device. And then you can CD into that directory and do an xsdev run device, and you point it to ESP32, and it'll find the one that's connected to your laptop over USB. And even without, if you just wanted to run an initial setup, then you could, without anything past the just xsdev setup, you can run it in a simulator and just start trying the code out yourself instantly. Now, future projects I want to focus on and start to really push the boundaries of what we can do with JavaScript on these embedded devices. So I wanted the ability to discover devices on a local network through web APIs. We heard a lot about installable web apps and being able to do stuff offline. I'd like to be able to expose that through web Bluetooth or web MDNS, maybe at some point, or web Wi-Fi, to be able to do that discovery and have locally installed web apps. Have an ECMA 419 compliant runtime on top of Node.js, so we can run on these embedded Linux environments like Node and Tessel with the same code that we ran on our super tiny microcontrollers. Having a HomeKit accessory protocol, also known as a HAP library for Moddable. Since we have HomeKit and HomeBridge for Node.js, let's make it just as easy to run on these tiny devices and make them look like any other integrated device on our network. And then securely expose those external services to the local network to get data. We saw a great example of this with Tiger's approach of using webhooks, integrating with Home Assistant, and then exposing that to his phones that he had running locally. And so things to check out after you're done with the conference and done with this talk. So this is the technical committee where you can find the ECMA 419 spec, where you can see all of our meeting notes and even learn how to participate and listen in on those meetings as well. This is the Moddable project itself, the open source code. Check out all the examples, documentation available there. This is XSDev, which is that CLI I was just showing you, over to get started and just start testing out this environment. And then J5E, the Johnny-Five embedded. So if you don't want to just do networking and start doing stuff with robots and be able to do remote control cars and boats and all this sort of stuff, check out J5E. Thank you, and happy tinkering.